Okay, moving on topics a little bit. If I have this horrible thing right here, and if we were asked to find the derivative of it, it'd be hard. It's a multiple rule problem. There'd be a quotient rule, a product rule, and a chain rule in it. Well, we now have a way to avoid some multiple rule problems. When confronted with non-logarithmic multiple rule problems, try what's called logarithmic differentiation. Now, I have a tendency, once I teach students logarithmic differentiation, they have a tendency to do everything by logarithmic differentiation. And introducing logarithmic differentiation when you really shouldn't have isn't necessarily wrong, but it will make the problem harder. Go with what I have there. Non-logarithmic multiple rule problems, like we see up there. So steps to logarithmic differentiation. 1, take the natural log of both sides. 2, simplify using properties of logarithms. 3, differentiate both sides, implicitly differentiating the log y. Multiply both sides by y, replace y with its rule. Okay, so I would look at this problem and say, yeah, it's a really hard multiple rule problem. I don't have logarithms. We will try log differentiation. So I take the logarithm of both sides. And then I start to simplify. Okay, quotient can split up by subtraction. And we'll call the square root of secant, secant to the 1/2, because with radicals, or with square roots, with logarithms, I like exponents. Don't much like radicals. Keep simplifying. And I'm doing this one small step at a time. So that product can be split up by addition. And then lastly, those exponents can come down in front. And now I'm ready to differentiate. We're differentiating with respect to theta. If you like x's, put x's over there, I don't care. But the logarithm, 1 over the argument, derivative of the argument, but I just differentiated something with a y. So instead of saying dy dx, since my variable isn't x, I'll put y prime there. But implicitly, 1 over the argument, derivative of the argument, 1 over the argument, derivative of the argument, but that it's implicit, so y prime. Over here, differentiating with respect to theta, so 1 over theta, 1 over the argument, derivative of the argument, 1 over the argument, so 1 over cosecant theta, derivative of the argument, derivative of cosecant is negative cosecant cotangent, minus 1/2, and we'll see if I can write small enough to get it on here, 1 over the argument, derivative of the argument. I'm going to have to rewrite it so I can get it all in one line there. Should have written just a little bit smaller. So back to this guy, 1 over the argument, then derivative of the argument, derivative of cosecant is negative cosecant cotangent, then I have my minus 1/2, then 1 over the argument, then the derivative of the argument, derivative of tangent, secant tangent. So let's just clean this up a little bit. So I've got 5 over theta. Here the cosecants are going to cancel, and I still have that minus sign, so minus cotangent theta. And here the secants are going to cancel. So I have 1/2 tangent theta. Then we're almost here. I want to know what y prime is. So now I'm going to multiply both sides by y. Because over here, the y and 1 over y cancel. And so I get y prime equals y times 5 over theta minus cotangent theta minus 1/2 tangent theta. And then lastly, replace y with what it was equal to. That just went off camera, but up there. So now I'll just put it down here. Recall that y was equal to theta to the 5th cosecant theta over the square root of secant theta. So just replace y with what is equal to. So theta to the 5th cosecant theta over the square root of secant theta, and then all that other stuff. 5 over theta minus cotangent theta minus 1/2 tangent theta. And there's my derivative done with logarithmic differentiation. But again, don't use logarithmic differentiation every time you see a product. If it's just a single product rule, use the single product rule. It will be easier. You want to use logarithmic differentiation when you're seeing god-awful messes there. Then logarithmic differentiation can help. If it isn't particularly messy, just do it directly with your basic rules. Okay, so we've beaten to death natural logs. Moving on a little bit. There are other types of logarithms, and we've talked about e to the x. There are other types of exponentials. So moving on to other logarithms, other types of exponentials, and we get this. The definition of y equal a to the x, a greater than 0, a not equal to 1. So a represents some sort of number. So just a generic exponential. And so definition from the mathematicians. For any number a greater than 0, a not equal 1, the natural exponential function with base a is a to the x equals ex natural log of a. Then just kind of a cultural thing here. Why do mathematicians use that as a definition? Well, okay, so we know, just going step by step here, we know that let's go in a little bit, zoom a little bit. Okay, so we know that e raised to the natural log of a is a. E's and e, the natural exponential and natural logs, inverse functions, when I compose them, they cancel, giving me the a. Then I can just turn that around and say e equals natural log of a, or a equals natural log of b. And then I could raise both sides to the same exponent. So raising both sides, giving both sides an exponent of x, we could say that. And then recall that for exponents to exponents, we multiply. And so exponents to exponents, I multiply. And so we get that a to the x must equal e raised to the x log a. So there's why mathematicians said this is the definition of what a to the x is. A to the x equals e raised to the x natural log a. Now you do not have to memorize that, but we are going to use it to find the derivative here. So find the derivative of a to the x. So y prime, I'm going to mix notations here. So y prime will be the derivative of a to the x, which will be then what the mathematicians gave us, that a to the x was ex natural log of a. We go with that because I know the rules for that. Natural exponentials repeat derivative of the exponent. Repeat derivative of exponent. Now remember here, let's note that x log a is the same thing as log a times x, and this is just a number, a coefficient. X is the variable. So when I go to do this derivative here, the derivative of x log a, which is the same thing as log ax, coefficient times a number, or coefficient times x, the derivative of a coefficient times x is just the coefficient. So again, where I'm getting that natural log of a. X log a, same thing as natural log of a, x. Natural log of a is just a number. It's no different if it was 12, 16, 92. 92, let's go with 92. If it was 92x, the derivative would be 92. But it's not 92, it's natural log of a. So the derivative of natural log of a times x is natural log of a. And then this is what mathematicians called a to the x. And so I get a to the x natural log of a. Now you do not have to remember how I came up with that derivative. Here it is in general. The derivative of a to the u is a to the u natural log of a du dx. Again, that's rolling in the chain rule. Whenever you see the u, that's implied that that's a function, so the chain rule is rolled into there. But here are the words. Repeats natural log of the exponent, or repeats, and we'll just go to the end. Repeats natural log of the exponent, derivative of the exponent. Those words work all the time, even for E. So if you can only remember one set of words. For E, I told you to remember repeats derivative of the exponent. For a to the u, different number base instead of E, I'm telling you repeats natural log of base derivative of exponent. These words work all the time, even with a base of E. So if you can only remember one set of words, here it is. Repeats natural log of base derivative of the exponent. And that's rolling in the chain rule. Now that's what I recommend you do. Learn those words. Repeats natural log of base derivative of the exponent. But you could do logarithmic differentiation on this. That would work. It's going to be a little longer, much easier. Remember that when I want to differentiate a to the u, it's repeats natural log of the base derivative of the exponent. Okay, we got time on this video for a quick one. So find the derivative of each of the following. And so my form here, and we now have to be very careful with form. It's a number raised to a variable. So my words here are repeats. Repeats, natural log of base, derivative exponent. So, repeats, natural log of base, derivative of the exponent. Repeats, ln of base, derivative exponent. Now I'll be perfectly happy and wonderful with that answer, but I'm going to do just a little bit of rewriting here. So I'm going to have 2 to the x squared. Like I said, I'm happy with that answer right there. But 2 to the x squared times, very specifically, 2 to the first times x times natural log of 2. So all I did was a little bit of rewriting. And I don't care at all if you do this, but I see it in my math lab. So I just wanted to alert you that my math lab does this. Same base multiplying, I can add those exponents. And so this becomes 2 to the x squared plus 1 x natural log of 2. Now I don't care at all if you do that, but I've seen it in the homework. But it's only possible because these had the same base, and thus I could add the exponents. And that's where we need to end this video.